Good morning. Here is the video on the biggest box that I promised that I would make for you all. I do apologize I didn't get it out to you before today. I was hoping to get it out by Friday evening. But here we are. We're getting it done. The question, again, several of you did ask about this, and then several others said that you'd already had this one completed. So either way, this is mostly for those of you that have questions about it. For those of you that have already completed this task, just keep in mind this might be a good review for you, and it also give you an idea of how I approach things as well. So what the idea is behind this problem is that you're given a piece of cardboard or a piece of paper, whatever the case might be, and you're wanting to remove the four corners by cutting out squares, and then you fold up the remaining sides to create a three-dimensional rectangular prism or a box that's open on top. And from the information that you have, you want to create a box that has the maximum volume. And so here is the example that I've come up with. We have a piece of cardboard that is 20 inches long by 12 inches wide. And we're going to remove the four corners from this piece of cardboard. So I'm just going to indicate this with these dotted lines. This is what we're going to cut out. Now remember that these are going to be of some unknown size, but they are going to be squares, so they will be equal. And so we're going to indicate the length and width of those corners by X. So what happens when we take this and we cut these corners out, I'm left with this edge right here that I would fold up. I would fold this edge in, I would fold this edge up, and I would fold this edge up. And it would generate a box that looks something like this. Do not judge my art skills. And so we would have this box with this open top. Now one thing that we want to note is the length of this box is not 20 inches any longer. We've cut out one square that's X units in length on the left, and we've cut out one square that's X units in length on the right. So now the length of this box is actually 20 minus 2x because we have removed these two pieces from that length. So similarly, the width of the box is no longer 12 inches. It's 12 minus 2x because we have removed these two squares that are X units in length. So the only thing that leaves now is the height of the box, and the height of the box is determined by the size of the square that we cut out, so it's just going to be X. Now if you recall, the volume for any rectangular prism is length times width times height. And in our case, we can substitute in all three of these values now, and we can come up with a polynomial that will generate the volume based upon any size x that we cut out of the piece of cardboard that we're looking at. So the length will be represented by 20 minus 2x. The width will be 12 minus 2x. And the height will be x. So I'll just indicate these right here. And we want to multiply these together to generate that cubic polynomial. So I'm going to begin, in this case, by multiplying these two binomials together. And we start off with 20 times 12 is 240. 20 times negative 2x is negative 40x. And then I multiply by this negative 2x here, so negative 2x times 12 is negative 24x. Negative 2x times negative 2x is positive 4x squared. And then we still have our height over here on the right. I'm going to clean up the interior here by combining like terms. So we have 240 minus 64x plus 4x squared. And then we multiply that by the height. So we're going to multiply all three terms in that first set of parentheses by the x that's in the second set of parentheses. And we get 240x minus 64x squared plus 4x cubed. this is our final polynomial for this particular problem. My mind wants to see this in descending orders of power, so I'm just going to rewrite this as 4x cubed minus 64x squared plus 240x. All right, so there is our polynomial. Just indicate it with that box. And now what we want to do is we want to find what's the value for x that if I remove that square from each corner, I will have the greatest possible volume that I could generate with this 20 by 12 piece of cardboard. So we could jump forward into calculus and we could start talking about finding critical values using derivatives, but we're not going to do that. What we want to do is just simply graph this using a graphing calculator and analyze that graph for the values that make the most sense. So we're going to jump over to Desmos and I'm going to graph this. We have 4x cubed minus 64x squared plus 240x. Now the critical values occur where the graph crosses the x-axis or where it changes direction. So we're looking at vertices on this graph, or let's go down here first. The first turning point in this graph is located right here. And when I click on it, you can see that the x value is 8.24 inches. Well, we already know that 8.24 inches, if I remove a square that's 8.24 by 8.24 inches, there won't be any paper left because the width of the paper is only 12 inches. And you can see that it has a volume of negative 129.94 cubic inches. So that makes absolutely 0 sense. When I go up here to the zeros of this particular polynomial, we see 0, 0. So if I don't take out any corners, I have a volume of 0 because it remains a flat sheet of cardboard. If I take out 6 inches, it will be 0. And if I take out 10 inches, again, it will be 0. So those three values make no sense either. So we're going to come up here to the final turning point in this graph. And I'll get up here in just a second, and it's right here. And that vertex is at x is equal to 2.42, 2.43 approximately. And it gives us a volume of 262.68 cubic inches. So that would be our answer for this particular problem. So I'm just going to come over here and write that down. That we have x is approximately 2.43 inches. And our volume will end up being approximately, need to refresh my memory on that, 262.68 cubic inches. Now what's nice about this is we can now use this on any size piece of cardboard, paper, whatever it might be, and generate a function that will have the maximum volume for whatever size square we want to cut out of those corners. And you can do that simply by just graphing it and determining those values. So I hope this clears this up. If it does not, please reach out to me. Send me a message. I'll be happy to answer that. I'm going to probably try to work up until about Wednesday afternoon, and then I'm going to take the rest of the week off. So I don't anticipate hearing from you, but if I do, great. It means you're doing some math over the break. It's awesome. If not, then we'll address it when we return to class on Monday. And I just hope you all have a wonderful break, but please, again, don't hesitate to reach out to me. And I hope to talk to you very soon.